implementing what is more commonly known as a feed-forward neural network. We're going to now finally create our first neural network. The problem that we're trying to solve, given a set of inputs and outputs, is to create a neural network to predict the outputs given the inputs. I took this example from IM Trask. His tutorial is linked below. And I thought this was a very good tutorial, but I thought that it lacked visualizations. So I decided to go ahead and add these visualizations based off of the stuff that we learned previously in the past 2 tutorials. So the way that this is going to work is there's a black box, just like the sigmoid function, just like the addition function, the multiplication function. There are 3 inputs and 1 output. The 3 inputs are as follows: x1, x2, and x3. If x1, x2, and x3 are 0, 0, and 1 respectively, the output is 0. If x1, x2, and x3 are 1, 1, 1, the output is 1, etc., etc. In this example, we're going to create a neural network with an input layer and an output layer, no hidden layers. And the reason for this is because I want to make it very clear about how these things work. And so what we're going to do is we're going to do a conversion from 3 inputs to 1 output directly. All right, so this is how it's going to look, the black box. There's going to be a multiplication with weights. A, B, and C are the weights that are added to x1, x2, x3. We're going to add all these up. We're going to push this through the sigmoid function, the one that we talked about in the last tutorial, and we're going to have an output. So what I'm doing when we're multiplying these and adding these all together, it's called the dot product of the vectors with the synapses. And so these are the synapses, A, B, and C. These are the synapse weights. This is what, when we're talking about a synapse weight, we're talking about A, B, and C. If you want to know more about what I'm talking about, go read IM Trask's tutorial down in the description below. But essentially, it weights the data x1, x2, and x3, and it pushes it through the sigmoid function to determine the output, 0 or 1, because that's what the sigmoid function outputs, and that's what we actually look for in these outputs. The output is, in fact, 0 or 1. So what is this useful for? Just off on a slight tangent, well, classification, right? Is this a dog or is this not a dog? Yes or no? And so if we have, pixel data, if we have other things, should I, trade the stock? Should I not trade the stock? And so if we're doing like stock-based training, it's very useful in the world of neural nets, but as you can see, there are more powerful techniques we will learn later. So in this neural net, feed-forward neural net, we multiply A times x1, B times x2, C times x3. We add all those up and we push them through the sigmoid. That's great. We know how to get the output. Problem is, alright, so first off I have an addition block with 3 inputs and 1 output. How does this work? Well, it's essentially the same thing by using 2 addition blocks to create 3 inputs. And you can see this, looks like this. Same thing, the backward propagation looks like this. We did an example like this at the sigmoid function. Take a look at that, take a look at this, and see if it makes sense. Alright, so these are, like I said, these are called the synapse weights. And these are randomly selected, and seeding a neural network means that we decide what these starting weights are. This is an entire science they're dedicated to seeding neural networks with these synapse weights. But for now, we're just going to center them around 0, right? -1 to +1, and then we're going to center these weights around 0. All right, we push them through. We randomly select synapse weight. We have our x1, x2, and x3. We push it through, and then we have an output. The output usually is not going to be correct unless we selected 1 for A, 0 for B, and 0 for C. If you don't understand why I said that, that's okay. But take a look at the inputs and the outputs table that I had previously, and you might understand. But if we randomly seed it, should not be the case. All right. So we have an output, and then we have an expected output. Our error is going to be the expected output minus our actual output we're getting from our net that's not trained yet. So how do we train this thing? Well, we use back propagation. Remember how we said DC was the pull we wanted on our function? Remember how we had all these DC values all the way up here? And then you're like, why the heck do we even have DC values? Well, DC values are the pull that you want on the circuit. Well, what's the pull you want on the circuit? It's the error, right? If there's no error, you don't want any pull on the circuit. If there is an error, you want it to pull on the circuit in the opposite direction in order to eliminate that error. That's the entire basis of neural networks. And if you can understand what I just said right there, where using the error function, we're able to eliminate, we're able to set DC, whatever this value is when we take the derivative, DC is the error, whatever that is, and we were able to set it, then we're able to say we're training this neural net to perform tests that we want it to do. And you'll see that actually. You'll actually see that. So right now I'm going to specify a value right there, value at location D. And this is important. This may seem a little off task, but just remember this value at D. It's going to equal x1 times A plus, x2 times B plus, x3 times C. That's the value at location D. And you can kind of understand that with the net that I created. All right, so remember, this is the value at D. Now, using the gates we created, update the values of A, B, and C using backpropagation. All right, so we'll set the error to DC, and then now we're going to calculate the derivative using these tables that we created for the synapse right here, this function right here. And so what is our value of A? Well, it's that location, the value of the location right here, and we said that value was D. I defined D to be x1 times A plus x2 times B plus x3 times C. All right, so that value D helps us calculate the derivative here. And then so that's great. Now we're going to backpropagate it and say, all right, well, the addition just kind of pushes all the derivatives through. That's the values of the derivatives at these locations. And then now we're going to say, all right, let's find the derivatives after the multiplication sign for the synapses, the inputs. But wait, we don't want to change the values of our inputs because they're held constant. Those are our inputs. Like I said, we can't change the image or the stock prices or anything like that. We have to leave those constant, which means those derivatives are 0. So the only things we can change are these hidden synapse weights. And these are the derivatives for those hidden synapse weights. And essentially the same thing as I did was take the derivative for the multiplication. As you can see, all the way on slide 2, I told you what the derivative for multiplication was. B times DC, A times DC. A times DC correlates to the derivative for B, and B times DC correlates to the derivative for A. If you still don't understand it, please look at my first video, and it should make sense. If it doesn't, please watch Khan Academy tutorials on derivatives, and I should post a link in the description below. Please remind me if I don't. All right, so now we have our derivatives for A. dA, dB, and dC. And the beautiful thing is, we can apply Newton's method to find new values for the synapses, A new, B new, and C new, and just by using a step size multiplied by the derivative dA, dB, and dC. Let me correct that. That should be dC right there. So, dC right there. All right. So, that's awesome. We've trained our neural net. And that's essentially the whole point of backpropagation. This is how it updates the weight, and then you can train your neural net to essentially do whatever you want it to do based off of your inputs and your outputs. Now, say that you have more complicated functions, and we'll explore those in the next tutorial after. Actually, it's the one after the next one, because the next one will be code for this tutorial that I have here. We will start exploring the possibilities of hidden layers and how you train those. But for now, we're going to do a simple backpropagation problem. We're going to write some code in Python.